Ever wondered how a simple click on your screen actually becomes an action? Well, the secret is language. Not human language, but these special languages we've built to talk to machines. In this explainer, we're going to trace that incredible story from the raw electricity of the first computers all the way to modern artificial intelligence.
So, here's our game plan. First, we'll get a handle on what a programming language even is. Then, we'll dive into the two basic worlds of code. From there, we'll start climbing a ladder through 5 different generations of programming. And finally, we'll pull back the curtain on the secret translators that make it all work.
Okay, first things first. Before we can track how code evolved, we've got to be super clear on our starting point. What exactly is a programming language?
This right here really nails the core idea. A programming language is, at its heart, a bridge. You've got human logic and ideas on one side, and on the other, you have cold, hard computer circuits. The language is that crucial link that lets our thoughts cross the gap and actually make the machine do something.
Now, sticking with our bridge metaphor for a second, it turns out they're not all built at the same height. Some are really close to the ground, right next to the machine's hardware. Others are way up high, much closer to how we think and talk. This distance from the hardware, that's a key concept engineers call abstraction. And this table just lays out those two worlds perfectly. On one side, you have low-level languages. They're all about the machine, speaking its language. On the other side, high-level languages. They're all about the programmer. They're built for us humans, making things easy to read and easy to write.
This brings us to the very first steps on what we'll call the ladder of abstraction. We're starting at the bottom, right down at the bare metal, looking at the very first ways humans ever tried to talk to a computer.
This timeline is pretty wild when you look at it. I mean, in just 40 years, we went from programming with literal ones and zeros to describing complex problems with logic. Each of these generations is a huge leap up that ladder of abstraction we were just talking about. Okay, so here's the absolute most important thing to get about this first generation. Machine code is the only language a computer's processor actually understands, period. It doesn't need a translator because it's the final destination. You could call it the native tongue of silicon.
And yep, this is what it actually looks like, just a stream of ones and zeros. To us, it's total gibberish. But to a specific computer processor, that exact string of bits could be a crystal clear instruction, like add these two numbers. The big problems? It's impossible for a human to read, and it only works on one specific piece of hardware.
As you can imagine, programming in just ones and zeros was a total nightmare. So slow and so easy to mess up. So that led to the invention of assembly language, the second generation. It was a small step up the ladder, but a really important one. The big idea was to swap out those raw binary codes with short symbolic words called mnemonics.
So for example, instead of typing a long, painful string of binary, a programmer could just write MOV AXBX to move some data around inside the processor. It was still super low level and tied to one kind of CPU, but for the very first time, the code was actually readable by a person.
All right, now we really start climbing. We've gone from unreadable code to cryptic code. The next bunch of leaps was all about creating languages that were truly designed for people, not just for machines. Third-generation languages were a complete revolution. The reason? One word: portability. For the very first time, you could write a program in something like C or Python, and it could run on computers with totally different hardware inside. This was huge. It worked because 3GLs hide all those messy hardware details, letting programmers just focus on the logic. This is the generation that built the modern world we live in. Most of the software we use every day is written in a 3GL.
The next step up the ladder, 4GLs, was all about making programmers more productive. These are what you call domain-specific languages, meaning they're built to do one thing really, really well. The classic example is SQL, for talking to databases. A single line of SQL can pull off a complex data search that might have taken dozens, maybe even hundreds of lines in a 3GL. It's all about getting more done with less code. And that brings us to the top of our ladder, for now anyway. With fifth-generation languages, the whole way of thinking about programming just flips on its head. Up until this point, every language was about telling the computer how to solve a problem, step by step. With a 5GL, you stop describing the how and you just describe the what, the rules of the problem, and the goal you want. The computer then figures out the how all by itself. This is the world of modern AI and logic programming.
Okay, so this creates a bit of a puzzle, right?
We have these awesome, easy-to-read languages like Python, but we also know that the computer's processor only understands one thing: raw machine code. So, how does our nice Python code get turned into the ones and zeros the hardware actually needs? Well, the answer is it needs a translator.
And this table here breaks down the three main types of translators. First, you've got the assembler. That one's simple. It takes 2 GL assembly code and turns it into 1 GL machine code. Easy enough. For all the higher-level languages, you've got two main flavors. You have compilers, which translate your whole program at once and spit out a new file. And you have interpreters, which translate and run your code line by line, right as it's happening.
Let's take a classic compiled language, C, as an example. The process is pretty straightforward. First, you write your code in a text file that a human can read. Second, you feed that whole file to a compiler. The compiler checks everything and translates it all at once, creating a brand new, standalone program. That final file is pure machine code, ready to be run by the CPU as fast as possible.
So if there's one big idea to walk away with today, it's this. The entire history of programming has been this steady, relentless climb away from the machine's world and toward our own. Each new generation just adds another layer of abstraction, hiding away more complexity and letting developers build even more amazing things.
And this whole journey just leaves us with a final, really fascinating question. We've climbed from telling the machine every tiny little step to just describing the problem we want solved. So, what could possibly be the next rung on that ladder? What would a 6th-generation language even look like? That's definitely something to chew on.